So again, we looked at 3 different models, right? Mediator, common cause, and common effect. And we looked at a mediator, and I said, well, you should only control for the mediator depending on whether you're interested in the direct or the total effect. And I said that you should control for a common cause to get an unbiased estimate of the true correlation between 2 variables, or true effect between 2 variables. And now I'm saying you shouldn't control for that 3rd variable if that 3rd variable is a common effect, if that 3rd variable is a collider. And I hope with the different examples that you get a sense of why conditioning on a 3rd variable, if that variable is a collider, could introduce a correlation that doesn't exist in the general population. Given the example of NBA basketball and the car not starting so far, perhaps that's not sufficient, so I'm going to give you another example. So perhaps you noticed this, I don't know, you've observed this and you wondered, hey, is there something systematic to my observation here? And that might be that if we look at at least the most visible, the most successful actors, right? So you have very successful actors who've made it in Hollywood, and they get paid a lot of money to appear in movies and such. I'm old school. I talk about appearing in movies and influencers and YouTube channels, etc. But sure, you can still make a lot of money by appearing in movies. And basically, you are successful because people like seeing you in movies. That could be because you're attractive to look at, or that could be because you're very good at acting, right? Probably there are more potential causes, but we're just focusing on those 2 potential causes of success in Hollywood, right? So if we did put that in a graph, and we're interested in whether acting skills have a direct effect on how attractive we consider people to be, we should consider that we're dealing with a collider again, right? Because if we're just looking at the people who are very successful, it's similar to the NBA example. If we just look at the people who are very successful in Hollywood, made it in Hollywood, that can only be the case if you're very good at acting or you're very attractive, or both. You probably won't make it in Hollywood if you're bad at acting and you're not pretty to look at as well. So basically that means that if we just look at people successful in Hollywood, we've conditioned on a collider. We've said we just look at people who are highly successful, and within that subsample of the population, there's a host of a lot of people doing acting, right? Not only in successful people in Hollywood. But if we just look at successful people in Hollywood, you might observe a negative correlation between acting skills and attractiveness, right? To the extent that if people become better in acting, they're less pretty to look at, and the other way around. That doesn't mean that there's an actual negative correlation between those 2 variables. It does mean that we observe one in the subsection of people who've made it in Hollywood. Because to make it in Hollywood, you can be both good at acting and attractive, or you can be good at acting, very good at acting, and perhaps not that pretty to look at, or very pretty to look at and not that good at acting. But you cannot be lacking in both departments, or you won't make it in Hollywood. So there's a selection basically to make it to Hollywood, and in that selection we might observe a negative correlation that is unlikely to exist in the general population. Again, an example of collider bias. So what we've seen is that whether you want to control for that 3rd variable depends on whether we're dealing with a common cause or a common effect model. And basically, the takeaway is that you should be very explicit as a researcher about your assumed relationship, the relationship you assume between X, Y, and Z, right? So sometimes talking about the same concepts, so the relationship between the amount of beer that is served at an office party, your evaluation by your manager of your performance, and how well liked the employees are by the manager, can be related in a way that you would call a common cause. You could also be related in which you would consider it to be a common effect model. So if your employer likes you, or your manager likes his or her employees, there's likely to be more beer at the office party, and it's more likely that you will be positively evaluated, or your performance will be positively evaluated. So if there's a positive correlation, or a correlation between the amount of beer and your performance evaluation, that doesn't necessarily mean there's a direct effect, because they could both be caused by a common cause, right? So it could be because your manager likes you, right? So they provide more beer and better evaluations. They could also be related the other way around, and you should be explicit about it, and you should argue well as a researcher why you think the one or the other is the case, because your choice whether you should control for the third variable or not depends on it, right? It could also be the case that depending on the amount of beer served at an office party, your manager starts to like you more, right? So you start drinking a lot of beer together, it's more likely that your manager will start liking you. If your manager evaluated your performance more positively, it's also possible that is the cause of the amount of liking by the manager, right? Because managers tend to like perhaps staff more that perform well in their eyes. So the causal arrow could also point the other way, and it's your role as a researcher to make sure that you are explicit about your assumptions. So what variables are included in the model, what variables are left out, and in what direction do the arrows point. And depending on the direction of the arrows, you're either dealing with a mediator model, a common cause model, or a common effect model. And depending on whether it's a common cause or a common effect, you should either control or not control for the third variable. All right. So, which brings us to the riddle we started with, if you can remember, right? So I talked about, perhaps inappropriately, perhaps a bit weirdly, perhaps I reminded you of a creepy uncle on birthday parties, and we started talking about his dating life on a weird moment in the conversation. But there was a point to it. Basically, we're better able to understand this example as a form of collider bias, right? So if somebody's observing that the people they date tend to get, this is from the translation software, they get more asshole. That's a weird translation. I'm sorry. People observe a negative correlation between physical attractiveness and, let's say, personality, quality of personality. I don't know how you want to properly put it, but the pretty people tend to be less kind, and the kinder people tend to be less pretty. And that's the correlation you observe in your subsample of people you've selected to go on a date with, right? Because you think it's important that the people you date are either attractive or nice or both, right? So in the subsample of people that you went on a date with, it's either the case that that person is attractive or that the person is nice to talk to, or both. But it won't be the case that both factors are absent. So by that selection process, you've introduced collider bias, right? So it doesn't mean that just in your sample of people you date with, in your Tinder dating life, you observe a negative correlation between attractiveness and personality. It doesn't mean that that applies to the population as a whole. You've introduced that bias correlation between the two because of your selection criteria. Because, again, you wouldn't want to date somebody who is both unattractive and an asshole, in this case. I'm sorry for the words, but it was already there in the slide. I will take it out. I don't know how it got in there. All right, so you could visualize that in the directed acyclic graph we talked about, right? So attractiveness and personality are both, they have a common effect, which is the selection of people, the people you select to go on a date with or not. And because of that selection, you might introduce a spurious correlation between two variables that doesn't exist in the general population. All right. Let's see. Yes, there it is. The takeaway from today. I skipped a couple of slides, and perhaps if you were so diligent in looking up the slides on Canvas, you might be surprised that we don't talk about some of the slides. I put that stuff in there because I really like talking about these examples, and I had some more we could have talked about, but seeing as it's already 3 o'clock and perhaps your brain is already fried, this is enough for now. We talked about the essence, and the essence is that when we talk about a cause-effect relationship, and you know how to be more specific about what we mean by a cause-effect relationship than just those 3 criteria: priority, exclusivity, and correlation of John Stuart Mill. But you know what an Innes condition is, right? And you know what we mean by the non-redundancy, and how we derive information about the non-redundancy by looking at counterfactuals in different type of research designs. We've also seen that researchers tend to be very ambiguous about the causal relationships they assume or the assumptions they're making in their causal model, because they're dealing with correlational data, and they've learned from their teachers during the studies that correlation does not imply causation. So I can't talk about causation, but I really want to, but I can't on the basis of my data, right? So it becomes very vague and ambiguous. And one way of solving that ambiguity is by becoming more explicit about your assumptions, by making it explicit in your directed acyclic graph, how you assume the different variables in your model, in your research, to be related. And depending on that relationship, so depending on whether you're dealing with a mediator, a common cause, or a common effect, you should control for different variables or not, right? And that's a more nuanced decision than just saying, I should control for any potential third variable in my data set, right? That's the purification principle, or overcorrecting, as Pearl mentioned it. And we've been more critical about that, and we said, no, you should only control for it if it's a common cause, right? And not if it's a common effect, because controlling for a common effect might actually introduce bias. And I hope you properly understand that final conclusion about not controlling for common effects, because of the different examples we talked about relating to NBA, Hollywood success, and perhaps even your dating life. Thanks for joining the lecture. I know it might be a challenging topic, but I hope it was interesting and it helps you to be more specific in thinking about causal relationships. If you have any questions, stick around. If not, I'll see you at the screening on Friday, and you'll see Sharon on Thursday to talk about correlational analysis.